If you probe two bar magnets, you'll realize that like poles repel and unlike poles attract. North-north repel, south-south repel, north-south attract. This is not dissimilar to how like charges repel and unlike charges attract. But how did this object, this magnet, exert a force on its twin across a distance? Well, it's because this magnet is surrounded by a magnetic field, a vector. You know, it's magic, it's the little magnet fairies. No, it's not, just stop interrupting. The magnetic field lines surrounding the magnet are drawn from the North Pole to the South Pole, always. Similar to how in the case of electric charges, the field lines are drawn from the positive charge to the negative charge. There are differences though between the two. Electric field lines span over infinite distances, while magnetic field lines are closed loops. You see, here the lines go through the magnet itself. And you can isolate a single electric charge, like this proton, in the middle of the universe. But you cannot isolate a north or south pole. If you cut this magnet in half, you won't be left with an isolated north and south pole. You'll be left with this. A magnetic monopole does not exist. Most magnets are made of iron because iron is a magnetic material. The reason it's one of the few magnetic materials that we know of is because of the behavior of the electrons present in the atoms that make up iron. The Earth itself is also a gigantic magnet. It has a north and south pole because it has iron in its core. And because of this, we can deploy compasses. Compasses are just needle-shaped magnets that point northward and allow us to navigate the seas. If you bring a compass near a magnet, the magnetic needle gets deflected. Okay, I'll talk to you later now. I'm getting late for physics class. Hello students, it's me, Professor Hans Christian Ørsted. Welcome back to physics class. It's the last one for this week as it's Friday, the 21st of April, 1820. So today, I'm going to demonstrate to you a finding of mine. Here, I have an electrical wire, and here, I have a compass. When I flick the switch, a current starts to flow, and boom, the compass needle deflects. When I turn off the current, it returns to its initial position. What do you make of that, students? I think this guy might be onto something right here. 100%. Can you show it to me again? What are you going on about? I did not understand anything. Again, I start the current and the needle deflects. I stop it and it returns to its initial position. The electrical current exerted a force on the magnetic needle. How? This experiment was a hint that electricity and magnetism had some connection. Indeed, electricity and magnetism are both different forms of the same thing. We also observed that a path of a moving electric charge is affected by a magnetic field. In fact, the strength of a magnetic field is defined by how much it affects a moving charge. After much probing, Ørsted came to the conclusion that the reason the compass was deflected by the current was because the current was generating a magnetic field just like the bar magnet. But the magnetic field lines are in concentric circles, with the wire at the center. So, it's undoubtable then. Electricity and magnetism are intertwined. It took time, but eventually we managed to unify the two forces into the electromagnetic force. This connection had many consequences at the time, paving an era for completely new energy production techniques. This was made possible by Michael Faraday playing around with electric currents and placing them in large magnetic fields. Hi, thank you for watching this video. If you feel certain explanations weren't understandable or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I have also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.